Conclude today with the second lecture of Dowker. In the marriage of discreteness and Lorentzian-ness, the matchmaker is randomness.
Thank you. So in this lecture, I'm going to try to justify the title. So I'm going to try and argue that without randomness, discreteness and Lorentzian-ness can never get together. Just to remind you that when I say discreteness, I mean combinatorialness. And just to point out that this was sort of embedded in the founding papers of causal set theory. So Jan Meerheim's original paper in 1978 that you can find only online because it was never published. It was a CERN preprint. Was called indeed statistical geometry. So here's the plan for the talk, today's lecture. I'm going to talk about the Poisson process, Poisson sprinkling. So those of you who were here yesterday for Raphael Sorkin's talk will already have been introduced to this idea in connection with causal sets. And I'm going to show you that discreteness together with Lorentz invariance implies non-locality of a very particular sort. I'll show you a picture. And then I'm going to argue that nothing beats Poisson. I'll say what I mean by that. And then say, well, we have some kind of theorem about this, but it doesn't really capture the full power of what we need in order to really be able to focus only on Poisson point processes. And I'll give you a conjecture about the Poisson process in Minkowski space. I'll introduce you to the Bombelli distance between manifolds, Lorentzian manifolds, and give you a conjecture. So this really follows on beautifully from the previous talk. So this distance between Lorentzian spacetimes is going to look very different from anything that's been considered, talked about so far. So I hope you're interested in it. It's super interesting. And I'll sketch the proof of a result that in the continuum limit of a Poisson sprinkling, you recover the full, the Lorentzian manifold with probability 1. I'll show you then finally that Lorentzian lattices fail to be uniform. And I'll contrast that with Riemannian lattices. And again, just to note that I'm going to be talking about random causal sets generated by a random process, but these are not, they're not physically, dynamically random causal sets or random geometries. So in Renata Loll's talk, the random geometries that she was showing you and describing results on, they're dynamically generated in a model of a physical process. So this randomness is not physical, it's kinematical. Okay, so I'm going to remind you of the discrete continuum correspondence between a causal set and a Lorentzian geometry that supposedly approximates that causal set. So, and I've replaced the Planck length just by some scale. I mean, actually the Planck length played no role at all. So that's a physical thing, but just mathematically it doesn't play any role in this proposed correspondence. So a causal set is well approximated by a Lorentzian manifold if there's a faithful embedding at scale L, embedding of C into M, which is uniform. The number of causal set elements embedded in any sufficiently large, nice region is approximately equal to the space-time volume of the region in units, in L to the D unit, so it's a D-dimensional space-time. It's order preserving, so X precedes Y in the causal set, if and only if the embedded points phi of X precedes phi of Y in the manifold. And the distance over which the continuous geometry, the Lorentzian space-time Mg varies, is everywhere much greater than L. So this is sort of you have to have this, otherwise the idea that you can recover continuum geometry from the discrete entity won't make sense. So does this hold water? Is it true that is it the case that all the geometrical information in a Lorentzian geometry can be encoded by this combinatorial discrete thing, the causal set? So here's one way to test it. We take a causal set that's faithfully embedded in a space-time manifold, and then we take M away, so forget M, just take C. Can we recover the geometric properties and values of geometric quantities on of M on scales large, this should be capital L, large compared to the scale of the discreteness, just from the causal set? Okay. Well, to do that, we need to get our hands on faithfully embedded causal sets, and that's where the Poisson process comes in. So, the Poisson process is a point process which we refer to colloquially as sprinkling, because it's just a sort of very physical way of imagining actually doing the process. You just drop points down into the space-time. This process produces a huge store of faithfully embedded causal sets that we can then go and investigate. So a d-dimensional space-time is a measure space. It's the volume measure that makes it a measure space. And there's a one-parameter family of Poisson processes in M. And the notion of a partially ordered measure space was beautifully introduced in the previous talk. So a Lorentzian spacetime is an example of a partially ordered measure space. And you can imagine everything that I'm going to say now being applied to this more general thing, a partially ordered measure space. And I just want to point out that there's a paper, a sort of mysterious paper, which is not a paper, on the archive by Luca Bombelli, by Johan Noldus, and a collaborator called Tafoya. And there's a very tantalizing abstract for this paper on the archive, but there's no paper there. But it's about partially ordered measure spaces. Anyway. You mean there's no figure? Yes, I think they retracted it. Anyway, but it's, anyway. Okay, so just a little bit about the Poisson process. It's one of the sort of basic random processes in maths and physics, and maybe only sort of superseded in importance by Brownian motion. So let NU be the number of points in some region U, which is under the processor, it's a random variable. And let V of U, VU, be the volume of that region U. Then the parameter, the one parameter of this one parameter family of Poisson processes is the density. So it's the expected value of the number of points. Oh, I stole my own thunder there. Okay. In U divided by the volume, so it's the, and it's Poisson distributed. So the probability of the number of points in any region being n is given by, region U being n is given by this Poisson distribution. Okay, and it's incredibly kind of restrictive and powerful condition that the Poisson process, restricted to disjoint regions of the manifold, are statistically independent. And that's according to Kingman. So all I know about Poisson processes comes from this book by Kingman. According to Kingman, the statistical independence is almost all that you need to deduce this Poisson distribution. So I never quite put my finger on exactly what else you need to assume, but if you assume statistical independence of the point process, then you can pretty much deduce this. So that's very, very powerful, that condition. Okay, so once you've sprinkled points down into your manifold, you then create a causal set from it by restricting the order relation of the manifold of the Lorentzian spacetime to that random set. This is a random set of points. So the Poisson process in M gives you a random causal set. In a typical random sprinkled causal set, which we also call a sprinkle, so we call the process a sprinkling, and of course the outcome of a run of the process also a sprinkling, confusingly. In the process with, oh, this again should be capital L, with rho is equal to, L to the minus D, is sort of by definition, if you like, or by construction, a faithfully embedded causal set at scale L. So the strategy is take your manifold M, sprinkle, get a causal set, pull M away. It's like, it's like when you pull the tablecloth out from under the crockery. You leave just the causal set there. It's this combinatorial thing. It's this graph. Can you recover the geometry of the manifold from C? So this is, I have to say, super fun and a rich source of master's projects, which is really great because last year I had 11 master's students. So there was a lot of sprinkling going on. Okay. Right. So what does it look like? Well, my goodness. So this is the outcome. It's a causal set that is obtained by sprinkling into, doing the Poisson process of sprinkling into two-dimensional Minkowski space. And you can see it's very non-local. This is the Hasse diagram. So the blue lines they're just one bit of information which says that the 2 points at the end of the line are related in the order. There's no length information here, remember, it's just combinatorics, it's just a graph. I've only drawn the covering relations, the irreducible link, the nearest neighbor relations. So for example, this point here labeled with the red arrow precedes this one, but there's no line drawn because you would not be able to see anything in this diagram if you drew all the relations. So these are just the covering relations. You can see it's highly non-isotropic, and that's of course because Minkowski space is highly non-isotropic. There are special directions in Minkowski space. It's just completely different from Euclidean space. Euclidean space becomes less and less, more and more featureless as you zoom in. But a Lorentzian manifold doesn't. It becomes like Minkowski space, and the null directions are special directions. And you can see them here. You can see it's highly non-local. So the two elements picked out with these green arrows, they're related by a covering relation, so they're linked, and there's nothing in the causal order between them. And I claim you can see here the essential structure of Lorentzian geometry revealed in a very revealing way. When you draw space-time diagrams, as we have been doing, you don't see you can't get your brain, well, it's hard to get your brain away from the Riemannian geometry of the piece of paper or the blackboard or even your brain. So you have to somehow kind of think and rethink and play tricks on yourself to really take on board the physical geometry, and the physical geometry is revealed in this way. So this point and this point are just as close in a physical Lorentzian metric as, let's say, this point and this point. Okay. So let me I'm going to illustrate that here by proving that in infinite Minkowski space, the number of covering relations to any given point of the sprinkling is infinite. Okay. All right, so let's take one point in the sprinkling into Minkowski space. Let's just consider the part of the sprinkling in its causal future. Okay, so, and just for definiteness, let's take it in the frame of the blackboard. So we've got t and x coordinates. Okay, so let's take the sprinkled point with the minimum t coordinate. That will be, that point will cover, let's call this one x0. So let's take x1 to be the point that that with the smallest t coordinate. That will be minimal. I mean, it's minimal in the future of x0. There's no element, there's no point sprinkled in there, so it's a covering relation. Okay, and now let's draw the hyperboloid of constant time-like geodesic distance from x0. So it's this space-like surface. It's got infinite volume, stretches up and up the light cone, and the volume in between this hyperboloid and the light cone is infinite. That has infinite volume. You can do that. It's a little calculation. So almost surely there will be infinitely many points sprinkled in here. So you take the one that's sprinkled in here, which has the smallest t coordinate again, and call that x2. And then you just repeat. So we draw the hyperboloid of constant time-like geodesic distance from x0 through x2, and then the volume between that hyperboloid and the light cone is again of infinite volume. There will be infinitely many points sprinkled into it. Choose the one of smallest minimum t coordinate. That will be, so x2 covers x0. There will be an x3, repeat. There will be an x4, repeat. So there are infinitely many covering relations. So it's highly non-local. As big as this diagram that you can draw, there will be covering relations that stretch from the very bottom left-hand corner to the very top right-hand corner. Yes.
X2 and X3 we pick the sprinkling that corresponds to the smallest coordinate within the volume type. I feel that there will be one that has the smallest.
There are infinitely many of them. So the only possible, either there's one with the smallest t coordinate, or there are two with the same t coordinate, but that has probability 0. So that has probability 0. Yeah. So with probability 1, the Poisson sprinkling is locally finite. Yeah, there's no accumulation point. Yeah. Okay. Right. So this is not a cuddly low valence graph like the one I drew in the previous lecture, but it's a really non-local beast. And I want to claim that continuum Lorentzian spacetimes are, if not actually non-local themselves, if you don't want to go that far and say that actually non-local things, then they're sort of teetering on the edge of being non-local. And once you go discrete, that non-locality springs out. Well, I suppose I mean that there's no kind of compact neighborhood of any point such that all the nearest neighbors of that point are contained in that neighborhood, something like that. So. Oh, you mean in the causal set itself? I suppose I mean in its relationship to the continuum, it's non-local. Via this embedding. So this embedding sets up this non-local relationship between the causal set and the space-time. That's set by the density. So a Poisson process has a density. That's the parameter of the Poisson process. So that tells you the expected number of points that are sprinkled in any given region is equal to the volume of that region. It's just the spatial volume. Yeah. Oh, sorry, space-time volume. Yeah. So it's regions like this. So in 2 dimensions, that's just area. In 4 dimensions, it's four-dimensional space-time volume. Yeah. Are there other
I
questions?
apologize if this has already been asked. I can't hear the questions in the audience, but your two green arrows are pointing between 2 points that have a single edge between them.
Yeah.
And the red ones don't have a single edge?
Correct. They are related, but they are not linked. There's no, they're not an irreducible relation.
I see, of course. I understand what you're saying. Got it, thanks.
Okay, are there other questions? Okay. So, question, could we reframe the discrete continuum correspondence to just say, and this appears in the literature, so sometimes the discrete continuum correspondence is stated in this way, right? C is approximated by M at scales larger than L if C is isomorphic to a typical Poisson sprinkling into M at density L to the minus D. There's this sort of weasel word typical, which of course has to be there because given a causal interval in Minkowski space, there is a non-zero probability that if you sprinkle at, well, even a very high density, you'll get the causal set that you sprinkle will be a chain. I mean, the probability is, so tiny, but nevertheless, you have to say that it's a typical sprinkling. Okay. So you can turn that question around and say, are there point processes that realize this number volume correspondence? In other words, the expected number of points in any region is given just by the volume times some density parameter with smaller variance than the Poisson process. Okay, so the Poisson process has variance which is equal to its mean. So the variance of the number of points in any region is also given by rho, the density times the volume. So the standard deviation has the familiar root n behavior. And we have a sort of theorem. So Sir Aslambaidi and Saravani show that there's no unit intensity point process for which the variance is uniformly less than Poisson for all regions. However, the conditions of their theorem is that this has to be true for all regions, no matter how small they are. But we don't care about regions which are smaller than the discreteness scale, because for the DCC, we want that the manifold is approximated by M only at scales, the causal set's approximated by M only at scales larger than some physical scale, which in quantum gravity is the Planck scale. But okay, so here's a conjecture. So there may be some variant of the statement of this conjecture, but roughly speaking, the conjecture is that there is no unit intensity point process. Unit intensity just means take rho is 1, so that the number of points in the expected number of points in any region is just given by the volume of the region. Okay, so there's no unit intensity process in a Lorentzian spacetime with d greater than or equal to 3 that has lower variance than Poisson for all, let's say, causal intervals with volume bigger than some v min. Okay, so slightly vague, but it could be firmed up a bit, but it's a conjecture. Okay, here's a second conjecture about Poisson, which is not to do with the process. And you notice that one could make this conjecture for any. It's just to do with the number of points. So it has nothing. This conjecture has nothing to do with the order relation. So you could make this conjecture for the Poisson process in a Riemannian manifold as well. It just needs to be a measure space. Okay. All right. And second conjecture does have to do with the order, and it has to do with the Minkowski space, the Lorentzian structure. So the second conjecture is that the Poisson process is the unique extremal Poincare invariant point process of unit intensity in 4D Minkowski space. So this little proviso here, that it has to be, that the condition is that it's an extremal process, is so to rule out things like, you know, you toss a coin and then with probability 1/2, you run a Poisson process of intensity 1/2, and with probability 1/2, you run a Poisson process with probability 3/2, right? That would have, that would be unit intensity, but it doesn't do what you want it to do, because you'll either get something which is sparser than unit intensity, or you'll get something which is denser than unit intensity. So saying that it's you want to rule those things out, so you make the condition that it's an extremal process. Okay, so that's also a conjecture. So note, conjecture 2 is false in Euclidean space. So for example, you could throw down sticks of some finite length, fixed lengths. So you have a whole bunch of sticks, you just throw them down into Euclidean space at random, their orientations are random, their positions are random, and take their endpoints. That's a point process. It's invariant under the Euclidean group, but it's not the Poisson process. And the key to understanding why there's a difference between the Euclidean and the Lorentzian cases is that in the Euclidean case, you can do the following thing. So run a Poisson process in Euclidean space. You have a bunch of points. Okay. Then for each point, draw a little ball around it, choose a direction uniformly at random on the ball, and put another point at that direction from the center, right? So choose that point, draw a little ball. So these balls are of some fixed radius. You choose again some random direction, that one, put a point there. So you can do that in Euclidean space. That's a process, it's not the Poisson process. It's going to have, you know, different statistics. So you can, but it's again the same obstruction to doing things in Lorentzian spacetimes. You don't have balls like this, nice compact little balls. You have highly non-local things like this. Okay, so this sort of way of producing point processes from the Poisson process that are not Poisson is not open, at least we can't think of one. So that's why it's a conjecture. So
basically, you're saying because the pseudosphere is known to act, our measure on it.
yeah, exactly.
The first conjecture, that doesn't imply metric, and one or
The first conjecture doesn't require, right, it could just be, it could be a conjecture for Euclidean space, for example. Yeah, Riemannian space. Okay. Right. Okay. So let me define for you a super interesting thing called the Bombelli distance. So let S be the set of distinguishing spacetimes of finite volume. And let omega n be the set of finite orders. That is, order isomorphism equivalence classes of finite causal sets. Then the Poisson sprinkling process of unit intensity in a manifold in S gives you a probability distribution on this omega n. So the idea is so here's your manifold, and you sprinkle, and then you endow the sprinkled points with the order relation that they inherit. It's a causal set with ground set the actual elements of the manifold. But if you take the manifold away, then it's an order. I mean, so this is equivalent to just some finite order. Okay. And if I do it again, so I do another sprinkling, I might get the same order, but it would be for different actual points of the manifold. So the same manifold, M and M, right? And I count this and this to be the same, right? So the Poisson process gives you a probability distribution over this set omega n, which is the set of finite orders. And as I was saying, the probability of any finite order in the Poisson process is actually non-zero. For most of them, it's very tiny. For finite orders whose cardinality is roughly close to being the expected number, that they will have relatively high probability, and the ones which are very far from that mean, that expected number, will have very low probability. Okay. But it's a probability distribution. So then the Bombelli distance. And for every manifold, every space-time, there is a probability distribution. So there's Pm and there's Pm primed for every manifold. There's a probability distribution. And there are lots of different distances between probability distributions at our disposal. And Luca Bombelli chose a particular one. He chose the Bhattacharya, I think there's a Y missing from the, misspelled this, Bhattacharya, angle between the two probability distributions, Pm and Pm primed. Okay, and it's a conjecture that, and we know no counterexample, that the Bombelli distance between M and M primed is 0 if and only if M is equal to M primed. So. Oh, yes. So take the probability distribution. The sum of the probabilities is 1. Take the square, make a unit vector from that, just a real unit vector, just by taking the square root of the probabilities. Each probability, just take its square root. That's a unit vector. And the Bhattacharya angle is just so for each probability distribution, you have a vector. Bhattacharya angle is the angle between them. So it's, yeah. Sorry, I didn't hear your question.
How do you make a vector?
Oh, yeah, okay. So, yeah, so let's say we've got probabilities P1, P2, and for our case, it's infinite. So we've got an infinite set of numbers. So this is the probability of causal set 1. This is the probability of causal set 2. This is probably, right? So you have a bunch of probabilities, and you make a vector. So let's call it P of P, root P1, root P2, root Pn, and then Vp dot Vp is equal to 1. So it's a unit vector. And so so this is some probability distribution P1. And then we have P2. It's just some set of probabilities, P1, 2, etc. And then V, and then P1, the distance between P1 and P2 is arc cos V P O P1 dot V P2. So I think the Bhattacharya distance is it's just this inner product between the two unit vectors, and then the Bhattacharya angle is just it's the inverse cos.
For example,
This one.
Yes.
Yes.
No, the one, like the first element of the vector, right?
This one, yeah.
So P1 would be the probability of one particular.
Yes.
Cause
So
of-
in fact, you can there's a count the orders, the finite orders, is a countable set. So obviously, well, there's the empty set. There's actually non-zero probability that in the Poisson process you sprinkle no points at all, right? So there's that, and then there's the causal set with one element. There's the causal set with 2 elements, and there's 2 of those. good. I should have done this, in fact. So here's the set of finite orders. And then there's the ones with 3 elements, so that's the 3 anti-chain. What we call the L, which is a 2 chain and an extra element. There's the lambda, there's the V, and then there's the 3 chain. And then there are the 4 element ones. So there's a finite number of orders for every cardinality. And the probabilities, these P's that come in this probability distribution, is just P of the empty set, the probability that you get the empty set when you sprinkle into this manifold, the probability that you get 1 element if you sprinkle into the manifold. Those will be the same for every manifold with the same volume. But then you start to get differences. The probability of this, what's the probability that when you do the sprinkling you get that? What's the probability that sprinkle that you get that? So for every manifold there'll be this list of P's, right?
Because you've restricted to finite, right, and because you've restricted to finite volume manifolds, the probability of having more than a finite number of points is 0.
Yep.
Yeah.
Yep. Thank you. Yes.
Just to connect this with the previous slide, because in the previous slide it said something like the typical process or something on the first line. So are you saying there's one of those that has like a probability clearly greater than the rest of them?
That's a very good question. So yeah, where does this probability distribution peak, right? And
I mean, the first line on this slide seems to suggest to me that it does peak somewhere, right? Because otherwise it's not clear what it means, right?
Well, suppose your probability distribution with this. It's really small, and then it goes whoop like this, and then it's really small. But the total probability of all of these ones is much bigger than the total probability of this one, right? Yeah. So in that case, this is not typical. You know, it may be the peak, but it won't be typical. When you do the process, you're going to get one of these, right? Okay. So it doesn't. It's a different statement.
But then different C's could be approximated by the same M, right?
Different C.
If you have 2 C's that
yes.
are both in the small probability region, they could be approximated by the same.
So anything that you can get when you do it on a computer, that's sort of by definition a typical one, because you got it. So it's got to be typical, right? So that's my working definition of typical, right? And there's lots of them. You get a different one every time. Yeah, absolutely.
Okay, thank you.
Yeah. I mean, these are subtle questions to do with, you know, what does it mean to be really random? You know, what's a random? You know, I give you a sequence of 1s and 0s. Is it random? Well, especially in the, you know, when it's a finite sequence of 1s and 0s, how do you tell whether it's random? And some things you can tell are obviously not random. If you just have 0, 1, 0, 1, 0, 1, 0, 1, that's not random, even though it's just as likely as a string that you would classify as random, right? So you'd have to talk about Kolmogorov complexity and, you know, what's the length of the shortest program run on a universal Turing machine that would spit out this thing. You know, I'm not. I'm appealing to your intuition, because that's all I have to say myself. Yeah. Are there other questions? Okay. Right. So this is a conjecture. It would be super nice to be able to say, to have it proved. But this whole sort of arena of ideas gives us a notion of, it gives us a concept of scale-dependent distance between 2 Lorentzian manifolds. And I'll just give you an example of what I mean by that. So let's take let's take the following two manifolds, right? So M1 will just be one-dimensional Minkowski space, which is time. And this is M1. And M2 will be a cylinder, flat cylinder. So it's spatially a circle cross time, right? Okay, that's M2. Now, and let's sprinkle at some particular density. If that density, and when you sprinkle into M1, you get a chain. No matter what the density is, it's just a chain. And if you sprinkle into M2 with a really low density, then you'll sprinkle a point here, one up here, and that will be a chain. So, and if it's a really low density, then almost all the time you're going to get a chain, and there'll be very small probability that you'll get a different. You'd have to sprinkle this, and then you'd have to sprinkle that to get something, a causal set that was a diamond like that. Right. So at low density, the probability distribution induced by M1 on finite orders will be very close to the probability distribution that is induced you get from sprinkling into M2. So they'll be these. Then you would conclude that these two manifolds are close to each other. But as you crank up the density, you start to see the structure. So in a very dense sprinkling, you're going to get causal sets. The two probability distributions will be very different. You almost never get a chain when you sprinkle into M2 at high density, but the probability distribution in M1 is entirely concentrated on the chains. So the distance between M1 and M2 will be very different, or will be much bigger when you when you choose a density which is high. So, yeah.
So somehow this difference that you're describing reminds me very much of sort of Gromov-Hausdorff distance on different scales in the Riemannian world. Is that where you're going with this? Or?
I'm not going.
I see.
No, I'm just, yeah.
So in other words, if I'm not wearing my glasses, they look like the same manifold. And now, depending on how good my vision is when I put my glasses on, I can distinguish the difference.
Exactly, absolutely. Absolutely. That's exactly what this distance which depends on the Poisson process, depends on causal sets, on orders, what it captures. So it's nice because you can, as in the Gromov-Hausdorff distance, you can compare manifolds of different dimensions. Is there
an obvious example that is there an obvious example that this distance is different than Gromov-Hausdorff?
I don't know the answer to that.
Well, Gromov-Hausdorff isn't really defined on Lorentzian in general.
Maybe like take all photographs.
But they don't know the solution. I mean, if this conjecture is still a conjecture, it means that we cannot answer to your question either, right? I mean, Gromov-Hausdorff distinguish non-isometric spaces, while here it's unclear. So,
but maybe one could simplify the question. Have you computed this distance for, let's say, the cylinder and the line? I mean, or at least an estimate. Or is it clear that it goes to zero if the radius goes to zero? I mean, if the distance between cylinder of radius 0 and the line vanishes in the limit, then
all these things would be really great to do. All I can say is that numerically, in terms of simulations, it's impossible to work with. I mean, you need to sprinkle, and count. You just need to, determine what causal set you've got, and then do it again, and build up some histogram, and it's just computationally useless to say. Yeah. But yeah, we know very little about it, I would say. Yeah, we'd love to know more. Okay, so let me move on a little bit from this distance. This is a different point now, which is that we know that in the infinite density limit, so this is not to do, we're really interested for physics, I'm really interested for physics in finite density. But you can consider whether there's a continuum limit. And in the infinite density limit, a Poisson sprinkling into a distinguishing spacetime gives back the spacetime with probability 1. And it relies on the Kronheimer-Penrose-Hawking-Malamud theorem. That's why this condition of distinguishing is in there. And in view of time, I was going to just go through that proof, but I won't do that now. Okay, so I think this, almost, it's the second to last slide. Okay. So I claimed that we need randomness to make the discreteness compatible, to make a discrete continuum correspondence compatible with Lorentz structure, Lorentzian spacetime. So here's an example that is more evidence for that claim. So it's the integer lattice. And when I say integer lattice, I'm going to show that the integer lattice does a very bad job of being an underpinning for Minkowski spacetime. So let's take this integer lattice in 4D. You can imagine these vertices being embedded in Minkowski space and decorate the edges with the Lorentzian edge lengths. So Lorentzian edge lengths are, 1 with an extra piece of information that it's space-like, and that's the time-like edge length is 1, but with an extra piece of information that it's time-like, and it's a combinatorial lattice. So you're not allowed to consider filling in any of the pieces of this lattice with pieces of Minkowski space. So they're very different from the piecewise flat manifolds that Renate Lal was talking about in her talk. So they're not manifolds. It's just a combinatorial lattice with edge length decorations on the edges. Okay. So this embeds consistently in Minkowski space, obviously, because that's how you've set it up. And by consistently, it means that the geodesic distance between the embedded vertices equals the decorations on the combinatorial object, okay? Or is very close to it, you give yourself a little bit of leeway. But it also embeds consistently in a gravitational wave pulse spacetime of the following form. So so ds squared is equal to minus 2 du dv plus 1 minus h of u dx squared plus 1 plus h of u dy squared, where h of u is equal to 0 for u less than or equal to 0 and u greater than or equal to 1 on root 2. So u is equal to 1 on root 2 t minus z. So this is a gravitational wave pulse. It's planar, it's moving in the z direction, and if you just stand there, it passes through you for a moment and then it's gone. And this integer lattice with these decorations embeds consistently in this. So I've chosen this wave pulse here so that it's 0 everywhere outside the blue region, and inside the blue region there's this constant profile h of u. And if you calculate the geodesic distances between the embedded vertices, then most of them are just the same because it's just Minkowski space. But some of them actually cross the blue region. You can calculate the geodesics, you can calculate their distances, and up to second order, they're equal to the Minkowski ones. So they're not exactly equal, but there's an order h squared correction only. So this the integer lattice with these decorations cannot distinguish between Minkowski space and this gravitational wave pulse space-time. There's no information in the combinatorial lattice and the edge length decorations that can tell you which space-time you're in. There's not enough information in it. It's too sparse. And the reason, and you might say, well, I don't care about this gravitational wave pulse because, if I'm standing here, it passes by me in one discreteness unit of time. So that's a space-time that is not valid in terms of the discrete continuum correspondence, because in the discrete continuum correspondence, you only care about space-times which have structure on larger than discreteness length scales. And you say this has structure on smaller than discreteness on the discreteness scale. But that's a trick of the frame that you're in. So in these coordinates, the wave pulse passes by you in one discreteness time unit. But if you boost, then what happens is, well, that the line through the origin remains where it is, but the future boundary of this blue region shifts. Depending on how big your boost is, you can make the future boundary of the blue region all the way out here, and the lattice points all bunch up. So they bunch up in the u direction, and they spread out. Sorry, v direction. And they spread out in the u direction, and you can consider a boost. So this is in t primed z prime coordinates. And in this frame, a boosted frame, the region in which the gravitational wave pulse is non-zero becomes very lovely. It's big enough to drive a truck through, right? You can make the height in t prime coordinates anything you like. You make it, a second or 20 seconds. And there are no points of the lattice in this region. It's a void. And so no wonder it can't, there's not enough information in the lattice to cover this and give you the geometrical information of the wave pulse. Now, the Riemannian integer lattice has no such problem. So if you imagine now, this is not Minkowski space, this is just Euclidean space. Have a lattice, take this region, fill it with a bit of non-flat Riemannian geometry. That space-time does have structure on smaller than on the scale of the discreteness, because there's no symmetry there's no frame, no physical frame in which you can look at it, which takes that region which has structure on the discreteness scale into a region which doesn't, because the Euclidean transformations are rotations. So you rotate this and it's still one discreteness scale thick, right? So the reason that this is a physically nice, perfectly reasonable space-time in the Lorentzian case is because of Lorentz transformations and Lorentz symmetry. Okay. So let me finish by saying the issue with the Lorentzian lattice is not that it breaks Lorentz invariance, or not just that it breaks Lorentz. Of course it does. Everybody knows that a discrete structure like a lattice breaks symmetries. It does break Lorentz invariance, just as the Riemannian lattice breaks Euclidean invariance in the Riemannian case. But the main issue, the issue I want to stress, is that the Lorentzian lattice fails to be uniform at all. So it just isn't anything like a Lorentzian manifold. It has huge voids in it, physically nice regions, which are kind of hidden if you draw the thing in the wrong frame, but physically nice regions are there in which there are no points at all. So it's not a uniform. The lattice is not a uniform distribution of points in Minkowski space, whereas in Euclidean space it is. It's a lattice distribution of points, which is a regular lattice, perfectly uniform in not perfectly, but is pretty uniform in Euclidean space. Okay, so the failure of uniformity for lattices, the success of Poisson suggests that only a random combinatorial causal set can be well approximated by a Lorentzian manifold. And then, if one wants discreteness, as I do, and some of my colleagues who want to base quantum gravity on it, then we just have to face up to this non-locality. We have to confront it and say how we're going to deal with it. How are we, in the face of this kind of structure, how are we going to read out geometrical information, like, for example, the Ricci scalar curvature? And that's what I'm going to talk about on Friday. So, thanks.